is about the light-driven micromotor, specifically bioinspired micro nanomotor with visible, uh, okay, sorry, with visible light energy dependent forward reverse, reciprocating, and spinning school in motion. Uh, First, let's talk about the background. In nature, many organisms can sense the intensity of an incident with visible light and habits by directional positive or negative phototaxis. For example, great energy and some married to practical and so in these movies. However, unlike the biological microorganism processing the bidirectional phototaxis, it's still challenging to achieve a similar uh, mimetic phototaxis for artificial micro and nanomotor. Uh, so far, great efforts have been exerted into the development of the artificial micro and nanomotor, and we are happy that a significant progress has been made in most aspects of these fields, especially in the light-driven micromotor. Up to now, several different propulsion mechanisms have been established in order to propel the micro and nanomotor by light. Uh, for instance, the efficient propulsion can be relied the best of bumbles generated through the photo irradiation enhance the counter-elliptic reaction. Uh, and the photo isomerization reactions. It can be also be achieved best of the Marangoni force are originating from the surf tension gradient, suffocation gradient caused by the photo dropping process or the suffocate released from the photo degraded light disposer polymer. And recently, some fulfill mechanisms have been reported. Uh, for instance, light-induced self-diffusive in this case, different ionic species origin from the photo uh, catalytic reaction have different diffusivities, with a proton inhibiting the largest fusion rate. So local electrical fields is established. Another case is the light-induced self-thermophoresis upon the light irradiation. The AU sites raise micromotor have higher temperature, thus forming a temperature gradient to propel the micro and nanomotor. Uh, Intuitively, a biodirectionally phototactic macro and nanomotor might be designed by combining two competitively light-driven mechanism that, of course, that must be both photoresponsive. Um, for example, self um, light-induced self-diffusive phoresis and light-induced self-thermophoresis. So, is there a possibility that we could combine these two classic mechanisms into the one micromotor to form a new mechanism? So in this work, two active compounds, the photocatalyst carbon carbonitride and the photodermal polypyrrole nanoparticle have been integrated into the correct micromotor. Specifically, the micromotor consisting the polypyrrole nanoparticle and carbon nitride and the gelatin excipients fabricating the emulsion solvent evaporation technique. And the micromotor is spherical in shape and size around 3 micrometer. Note that minimum concentration of the galaxy excipient inside the micromotor have to be the 10 percentage to obtain the spherical shape of the micromotor. So when operator radiation, we observe the unprecedented light energy dependent for the taxis. You can say these movies. Okay. Under weak light irradiation, this micromotor social positive for the taxis and move toward the light. When exposed to the strong light, the micromotor negative for the taxis, namely is move away from the light source. There is a threshold of light intensity. It is 0.8, at which the micromotor only exhibits the brownie-like motion. Let's think again these movies. Okay, first it's exhibit positive and it's negative for the taxi, and it exhibit brown-like motion, and it has been reciprocating motion. Okay, we find out that the correlating micromotor even exhibits the unique reciprocating motion by simply adjusting the light energy during this process. I can be this movie. The micromotor first move towards the light source. After around the 4 seconds, as the light energy is increased, the micromotor slowly declarates stops, then change its direction and move away from the light source. Let's see it again. Okay. Sorry. Again, positive for the taxis appearance under the 0.4 to 0.8 irradiation with a movement speed increased at first, followed by decrease. Note that the self-person traveling under very weak evolution power. A negative phototaxis appearance when the micromotor senses the evolution stronger than the 0.8 and its speed increase with the irradiation intensity. Okay. Under the under the irradiation, changer separation, oxide or carbon nitride. Carbon nitride is a well known igno, igno, polymeric photo catalyst, which is capable of hydrogen water based on photocatalytic reaction. Uh, in this equation one, the electron are injected into the polypore nanoparticle. The electron with oxygen inside the solution, leading to a formation of the superoxide radical. While the host, while the host, uh, they act with water, resulting in the potent and the hydro radical. This is equation 3. So different ionic species have different diffusion rates, with proteins exhibiting the largest diffusion rate. So, uh, as a consequence, the local electro fields is established and can be seen in this simulation. At the micromotor, which has a negative so charge on its surface. Uh, Therefore, which is propelled to the light source by these electro fields based on the self-diffusion mechanism. On the other hand, the negative phototaxis motion arising from the self-thermal phoresis caused by the photothermal effect of the polar poro compounds or into this broad light absorption band in the visible range and the light to her heat correction compatibility. You can see this picture, the temperature and the water and the liquid or liquid and the micromotor interface is enhanced owing to the photothermal effect, and the temperature decrease gradient the temperature gradient gradually across the micromotor due to the weak thermal conductions of the micromotor. So the self the morphoretic force Ft is proportional to the self generated local thermal gradient, and this equation. Where Kp is Boltzmann factor, delta T is the temperature gradient, and alpha T is thermal diffusion factor. In the most situation, alpha T is positive. So the self-thermophoretic force is against the thermal gradient. Um, so the temperature gradient so drives the negative phototaxis and phototactic motion of the current micromotor. To better elucidate the motion mechanism of the micromotor, you can see these movies. It only exhibits the positive, negative phototaxis. We used it to the model to quantify the self-thermal phoretic and self-diffusion ferritic force. Among others, the most of the carbonated PT-based micromotor exclusively based on the self-diffusive phoresis, and so this below movies. You can see it and it's only exhibit the positive for the taxis. And we have recorded the self-propelling velocity relates to micromotor under the different light energy flows. And we also estimated the corresponding the driving force by utilizing the Stokes equation. This relation curve will be experimental observation. Notably, there is interaction. You can see interaction between the two currents at the light about the 0.8, below which the self-diffusive force dominates. Otherwise, the self-thermal ferritic force dominates. At the point of interaction, the self-diffusive ferritic and the self-thermal ferritic force roughly balance each other. So it can be concluded that these two mechanisms exist in the micromotor, and it's the dominant mechanism that determine the motion behavior of the carbonated and the polypropylene-based micromotor, namely weak light self-diffusive forest dominates, and under the strong light self-thermal forest dominates. Okay, we also observe a group micromotor. I can see its movies under a weak emulsion. There's a priority for the taxis, and under a medium intensity of light, they only exhibit the browning-like motion. When we turn up the light intensity, they arrive from the light source. Namely, they exhibit the priority for the taxis. Just like this scheme illustration. And this collective behavior are similar with this behind the single micromotor motion. Behind underlying the mechanism is competitive with the self-diffusing phoresis and the self-thermal phoresis, which can be confirmed by this picture. Okay, the collective phototaxi can also be observed at the microscopic scale. I can be seen from the movies. the carbon nature and polypropyl based micromotor move towards the side walls over the queer counters, and no, it's imperative for the taxis. Oh, okay. When we turn up the intensity of light, it's the negative phototaxis. So uh, it's also it's also presents the microscopic property for the taxis and the microscopic negative for the taxis. Uh, okay, the above case we just discussed is under the paralight. Another interesting question is what happens under the diverse light. This is the schematic diagram of the divert light port. Uh, you can see this picture. Divert light port from the top view, and the right picture is the intensity distribution from the beam center along the dashed line in this picture. Okay, we can we can what happens? We can see what happens. Okay. Similarly, they also under the low intensity um, 0.4, they also uh, exhibit the particle for the taxis under the divert light. And under the high intensity of light, 1.2, they saw the negative for the taxis. Okay, include under the weak and strong light, the micromotor so the collective positive and negative for the taxis under a diverse light as expected. Um, on the other hand, since the light intensity directly determines the phototactic behavior of the present micromotor, could interesting phenomenon be expected if we employed the no uniform divert beam having a wide range of intensity that covers 0.8? Um, it is it is very important because in this point the micromotor only exhibited the Brownian-like motion, and below which a micromotor exhibits the property for the taxis, and moderate micromotor so the negative for the taxis. So if we have a red range of intensity that covers 0.8 and 1 and the 0.6. So what happens? This video, the local light intensity dependent for the taxi related to unique spinning schooling behavior of the micromotors. In other words, we observe the unique spinning schooling behavior of the current micromotor. I think I think it resembles the schooling behavior of fish swarm. Okay, it's a fish and it resembles. So okay, there are the overlaid optical microscopic images of spinning schooling motion and the representative trajectory of micromotors at the different preparation during spinning schooling motion process. A micromotor close to the vortex center, this blue color, moving in cycles with a low speed around the 3 micro, and the micromotor speed increase the distance to the vortex and reach the 8 micro at the vortex per ferret. And it's green color. Okay. Okay, so how to understand the mechanism of the linear spinning collective behavior? The light intensity distribution is roughly is the best of the vortex size and the profile of the derived light intensity. A micromotor at the Horizon 1 at the figure experience light intensity for the taxi of 1 and exhibit the negative for the taxi. At the Horizon 3, the micromotors are positive for the taxi because the local intensity in this area is around 0.6. At the Horizon 2 in figure, where local intensity is around 0.8, the micromotor exhibits the browning light motion. Moreover, light beam can loosely trip the micromotor as the micromotor near the beam periphery move towards the beam center due to the positive phototactic and inter-particle diffusion phoretic interaction. Consequently, the ensemble micromotor effectively experience the collective Tokyo and the Haze spinning clockwise. Furthermore, a coarse-grained dynamic simulation has been performed to reproduce the spinning schooling behavior. I saw in this movie, which is consistent with experimental results. Okay, in summary, we innovatively combine the self-diffusion phoresis and the phoresis mechanism to achieve the visible light-driven micromotor. And biodynamically changing the light intensity, the micromotor experiences the reciprocating motion and under the finely turned no uniform beam, the group of micromotor exhibits the unique spinning schooling behavior. At last, we access to all the answer to this work as well as 3 professors, Prof. Dong from Soochow University, Prof. Yang, Institute of Physics from the Institute Physics Chinese Academic Science, and Prof. Dong from South China Normal University. And okay, that's all.